Okay, thanks, Michael. So I'm Kristal, and I'll be talking about PIQL, which is a performance insightful query language. This is a result of the effort of many students and advisors, so thank you. And so where this fits into the RAD Lab architecture is here kind of an interface between the system and the developer. So the idea is to provide feedback about the application to the developer as they're working on their application. So the motivation for this work is that we've observed over the past couple of years that websites are growing in their popularity at an amazing rate. So a couple of examples. One, Twitter is growing in their utilization from just over a few years, from just starting off to this exponential growth to now they're serving in the tens and up to 100 million tweets per day. So this is a very amazing rate of growth, and it's really causing a ton of re-architecting, and it's causing a lot of work to try to keep up with this growth and load. Also, another shorter-term example is recently we had this app called Animoto, which would create a music video if you uploaded a bunch of photos and a song. And they saw, using Amazon EC2 for their app servers, they were able to scale up from just a few to several hundred app servers in just a few days because they grew in popularity so much. So one thing that makes this very challenging, though, as apps are trying to keep up with this amazing rate of growth, is that they've really got to keep amazing performance even as they're trying to scale. So, and what some people have discovered is that even a very small change in the order of a couple hundred milliseconds can drastically reduce user interest in your website. And very few of us now use Friendster as opposed to Facebook, and this is because they were unable to scale with the demand as they became more popular, and they just kind of stepped aside as Facebook took over. So as the developers are actually trying to scale these apps, one thing that we've noticed is, of course, scaling the app tier is very easy. We just add machines. But what's often difficult about scaling these applications is that using a full database doesn't really lend itself to these scales. And a recent example of this is that Twitter admitted at their Chirp conference last year that many of their infamous fail whales were actually caused by database queries that they didn't realize would be slow as their user base grew. So what's happening now is that many websites and the developers are just leaving these databases behind and producing these NoSQL solutions. And many of the large web properties that we're all familiar with have taken this approach. So, but it's important to remember that full databases were actually designed to provide some very important advantages that are being sacrificed by this move. So full databases provide a declarative interface to writing queries that hides a lot of the mess from developers. So this means that the optimizer makes all the decisions about how to execute the query. Also, the physical and logical data independence mean that the queries can stay consistent even as the underlying storage system changes. And also that they get parallelism for free because that's just happening underneath the surface for them. But the penalty, of course, for having this convenience is that you have some performance opacity. So you can write a query that seems fine. It's delivering great features to the application, but as the user base grows, this can break things. And this seems to be what Twitter is experiencing. So what's happening now is even if the web properties are not abandoning these systems, they're often using them just as a key value store, and they're adding some kind of ad hoc caching layer or management layer above them. So what's also happening with the NoSQL system is that you have this kind of cumbersome, simple query interface. So rather than being able to just specify a query, you have to use imperative programming to issue requests against the narrow interface for this key value store. And every time something changes, the indexes have to be updated, the queries have to be changed. So these things are very brittle. And Michael mentioned during the intro talk that the undergrads really had a lot of difficulty programming against these key value stores. And it seems that this is a pretty common experience through industry as well. However, what makes these so attractive, even though they're more cumbersome, is that since they have a narrow interface, the simple operations have a more predictable latency. And it's a lot easier to spot when something is going to cause a performance problem. And again, this is distributed over many nodes to the key value store. So clearly, the NoSQL systems are providing something that's attractive, even though they're sacrificing some of the convenience of full databases. So the idea of PIQL is to position itself somewhere along the middle of this spectrum and gain some of the advantages of each of these types of systems. So we'll maintain the declarative nature of SQL, and that the queries that developers write are independent of whatever's going on with the storage system. However, we do require that the developer provides an upper bound on how many records that the query will be able to touch, even as the user base grows. And so in return, they get the optimization behavior that they're used to. And also, the NoSQL systems provide nice performance insight into the system. So the idea of PIQL is to provide feedback as the application developer is working on their app about which queries will either potentially touch an unbounded amount of data and will continue to become more and more expensive as the user base grows, or just which queries are unacceptably slow, given that, as I mentioned earlier, the latency has to stay within a few hundred milliseconds if the application wants to retain its users. So some other features of PIQL. As you're planning to be able to provide a scalable app, you know that your data sizes are going to continue to increase, and you have to maintain an SLO around the hundreds of milliseconds. So the system, since, as the undergrads mentioned when they were demonstrating their apps this morning, since the queries are all pre-specified, we are able to automatically produce indexes and also the materialized views so that the computation can be saved at runtime. Another principle of PIQL is that since it's a library that's executed on the app tier, the key value store underneath can be one of many choices. In this case, we're running on top of SCADs. We just require a few operations that the key value should support. And also, as Justin will talk about more, this also allows the possibility for any queries that are impractical via PIQL to be executed via various analytics frameworks, or you can also drop down and write the query yourself if you want to. But so you're not really losing anything over the approach now where people just write all the imperative queries. That's still an option. So another feature of PIQL is that since developers are constantly changing the feature set that's available with these applications due to the high rate of churn with these software as a service properties, is that we want to support schema evolution. So one schema may be adopted at first, and then as features are changed, the schema will also change. So using Avro serialization, you can support these things coexisting in the same storage system. And also, of course, we want to support different versions of the system being rolled out. So that's also something that can be provided with this feature. So another thing about PIQL, as I kind of mentioned earlier, is that we do require that constraints be specified with the queries. And we've noticed through some examples that we've seen in the popular web properties that many applications either have natural cardinality constraints or they can certainly tolerate cardinality constraints. So, of course, many of us know that Facebook only lets us have 5,000 friends, but most of us don't hit that limit, so that's okay. And also, a Twitter page size just displays, in the tens of tweets, and then you can always page to further points in the more remote history. So we want to take advantage of this fact and use that to annotate the queries that are provided by developers. And this, as Michael mentioned in the question period from the undergrad's talk, this allows us to retain joins. So this really is a boon for the expressiveness of the language, even though it's limiting the work that's happening to provide the performance safety. And so then the optimizer leverages those cardinality constraints to give the performance feedback to the developer. Because developers, we've noticed that they really like to think in terms of adding features to their applications, but they don't have the practice of thinking in terms of what features would be compatible with good performance, at least the Elvis developers that we're targeting with this technology. So I have an anecdote here because, of course, Facebook has this cardinality constraint, but one of the users that was actually hitting that cardinality constraint of 5,000 friends, a tech blogger, Robert Scoble, noticed that even though he hadn't reached the 5,000 constraint yet, a little while ago, when he had 3,000 friends, things were still slowing down for him. So this is a good example because even though Facebook did specify a cardinality constraint, the cardinality constraint may have not been appropriate with the performance that they were trying to provide. So, and another example of this fact is, this is a graph that we took from one of our practice runs of Scatter. Scatter is the Twitter clone that you guys have been using. And what we noticed is here, what we're showing is the 90th percentile latency observed at all the PIQL servers. And on this left part of the graph, you see that in this case, the undergrads had specified that each user could have 5,000 subscriptions. And you see that initially the performance of the queries is fine, but then as the experiment progresses and as the user base grows of Scatter, the query latency continues to also grow. And so this is a good case of where, the developer did the right thing by specifying a cardinality constraint. The query was working fine when the app was getting off the ground, but as the app continued on in gaining popularity, it started to slow down. So what we see on the right part of the graph is that this led the developers to change the cardinality constraint. And then that had a dramatic impact. And you can see that even as the user base grows toward the right side of the graph, the performance is staying constant. And that's one of the big goals of PIQL, which is that if your app works when you have a small user base of just your friends, it should continue to exhibit the same performance as the app gets millions of users. So the goal here is to provide this module called the Performance Insight Assistant. And what happens here is that if the developer submits an unbounded query, so this is an example of an unbounded query because we don't limit the number of users that can follow any other particular user. And of course, Oprah would have a lot of followers. So this query would just be rejected from the system. But but even if the developer submits a bounded query, we would provide some insight into how the cardinality choice that they had specified would impact their latency. So then you see on the right side of the graph, we have a cardinality and latency graph. And if we are also provided with the SLO, then we can specify the region of the graph or the range of cardinalities that are acceptable for this application. And I should note that we have some ideas about what to do in the uppercase as well. So you can, as I mentioned, the pre-computation. So this case can still be handled, but this wouldn't be a query that would be executed in real time. So some of the assumptions we're making here is that the storage system is correctly provisioned, and so it's able to meet its SLO, which is the latency on the low-level operations. And so Beth will talk more about how she's able to ensure that the storage system is meeting the SLO. The other assumption we're making here is that since you're not getting SLO violations from abnormally long requests at the storage nodes, you're probably getting them from these people who are hitting the high cardinalities. And often these so-called super users are the ones who are posed to make the most noise and complaints about your app's poor performance. So we argue that you really care about meeting your SLOs for these super users. So what we've done here is we've looked into Scatter. And the queries for scatter fall into 3 cases. So for some of the queries, no limits needed because it only touches 1 record, independent of the data size. For some of the queries, 1 limit is needed, and for some, 2. And so I'll walk through that a little bit more, but we're going to talk about the latter 2 cases, and one of each of those cases. So my subscriptions just gets all of the user subscriptions, and then the thought stream gets all the users to whom you're subscribed, and then gets a bunch of their thoughts to produce the thought feed or tweet feed that you see on your scatter landing page. So the setup that we did, we used deploylib, which Andy talked about. So we were able to deploy scads on EC2. We have 5 storage nodes. And this is just because this is kind of preliminary work exploring this space. And we have also some plans about how to develop this future in the future. And then we have 1 trace collector for each of the queries. And the PIQL library runs on the trace collector. And then we have some data loaded in. So the scatter queries that we're looking at here, we have the my subscriptions. And as Alan mentioned earlier, it has kind of a link syntax. And you see here that the limit has been specified. And with ThoughtStream, we have 2 limits. So first we have to limit the number of subscriptions, and then we limit how many thoughts are shown on the page. So in this case, this is an example of what a cardinality benchmark would look like for a query with 1 limit. We vary the cardinality, and then we look at the latency at a few different quantiles. And usually the tail quantiles are very interesting, so we definitely want to look at those. But what we notice is that this query is very inexpensive, even at a high cardinality. So we really don't care what we choose for the cardinality of this query. It's not going to be an expensive query in our system. And so you could imagine that this type of analysis would really help the developer focus on which queries they need to think about more and which queries would be a potential issue for the scalability of their app. Now, in the other case, what we have here is, since ThoughtStream has 2 limits, the number of subscriptions and the number of thoughts that are shown on the page. So you see those as the 2 axes on the base of this graph, and then you have the latency on the vertical axis. So what we have here is a surface, and this is the this is actually, this is the 99th percentile latency for the ThoughtStream query. So if you say that your SLO on this query is going to be 300 milliseconds, then you can draw a line at 300 milliseconds on the surface, and then you know that this would be the region of acceptable cardinality pairs for this query. And so that would really give the developer guidance about how to set those cardinalities, because it's been our experience working with our undergrads that sometimes they don't really have a good feeling for what the cardinality value should be off the bat. They sometimes just put an arbitrarily large cardinality value there just to get it to compile, and they don't really have a good process for coming around at that. So the point of this is just to guide them to a more reasonable value. And especially in these cases where you have multiple input parameters, it can be very helpful to have a way to reason about this space. So the next things that we're thinking about are modeling each of the PIQL query operators, and then for various combinations of the parameters. And the nice thing about PIQL is that we know all of these things at the point of the app development, and we have some guess about the data size based on developer information. So this modeling process is pretty straightforward. So what we're also thinking about is how to compose these models to provide predictions of the overall query latency. So this would kind of replace the actual sensitivity analysis of the cardinality. So that's the direction we're heading in. So just to wrap up, the idea here is that PIQL gets the good aspects of both sides of the spectrum with databases to NoSQL systems, and that we retain the declarative nature of the queries. We maintain the performance insight that developers get from NoSQL systems. We also provide means to support analytics and user-defined queries and allow for the schema to develop as the app goes through iterations. And again, I've shown how the Performance Insight Assistant can actually give you some ideas about how to set the cardinality values so that you don't just produce an arbitrary upper limit, and we're still working on developing that to include some modeling. So thank you. I'll take questions.
So I like the idea that you're able to draw a graph that shows the SLO violations versus cardinality. But in some cases, limiting the cardinality is going to seriously limit the functionality of your system, right? Like Facebook, where you can only have 100 friends, is a much less interesting platform. So it seems to me that what would be really interesting would be to find a way to put another axis on it, which is applying more money to the problem, right? Because of course, if Facebook was faced with the problem that they couldn't scale beyond 100 users, they would throw money at the problem because it's their business. And telling people, that you can't have more than 100 friends is going to push people back to Friendster or MySpace or whatever. So that might be an interesting place to think about future work too.
Yeah, certainly. I mean, so as I mentioned, we're kind of assuming that the underlying storage system is kind of already provisioned and that's kind of fixed. But I think if you did say, oh, this cardinality value is unacceptable, then I think it would be the right thing to go down a layer and say, okay, we've got to change things here. We've got to change the storage solution, that sort of thing. So, and also what we've thought about is kind of having a differentiated service where, maybe most users have small cardinality values, but for the most expensive users, you dedicate extra resources to hitting them. So that could alleviate some of that.
And just to add to that, one thing that we're considering looking at as part of the AMP lab is this idea of aged pickle. So right now, what Kristal's describing is kind of this, you run all of the queries, as they're asked. But aged pickle is the idea that you could also leverage pre-computation to allow you to kind of run queries over these higher cardinality values where the results might be a little bit stale, but at least you can still run the answer. Yeah. Cool. Any other questions? Okay, then I think we're going to hand it over to Beth, who's going to tell us about the underlying key value store.